Welcome to Algebra 2, Unit 6, Lesson 7, Logarithmic Equations Part 2. We do have a guest with us this evening in our lesson. He's very cute, and he's probably also going to get bored sitting on my lap. So I might have to kick him off because he's kind of on my hand, which makes it hard to do this. So without further ado, let's get into Logarithmic Equations Part 2. We are going to cover a little bit on financial applications after this lesson. I'm going to piggyback it with some review, at least this year, the year that I'm recording it. That's what the plan is. And then this is our last lesson that presents not even new material, but the merging of some previously learned material together. So we're going to start by recalling the two strategies for solving logarithmic equations. This means you have to go back 3 class periods. The last 2 class periods, we've been dealing with the properties of logs, and we did a discovery activity where you used your calculator to discover what the properties are, and then we had a separate lesson where we summarized that and then looked at how those properties play out in different kinds of logarithmic expressions. Then before that, we covered the 2 strategies. Now we're going to come back to those strategies. So the first strategy is to change it to an exponential. So when does this work? This is good for when there is one logarithm that can be isolated. Okay, so if you're looking at your equation and there is one logarithm and you are able to get that logarithm by itself, then this is a good strategy to use. Now, it kind of depends on what's on the other side of the equation, but this is certainly something that you would want to try. So kind of keep that in mind. One logarithm, change it over to an exponential. And the way we do that is, of course, using this log base b of n equals x, and then you could change that to b to the x equals n. It's the opposite direction from when we first learned what logarithms were. The other strategy is to set the arguments equal, okay? And the argument is what you're taking the log of, okay? We don't want to have what Mr. Frenzel might call a naked logarithm, okay? So if you have a log, it has to be taking the log of something. It's an operator. So just like if you saw a square root in the middle of your equation, okay, and somebody said solve for x, you'd say, I can't do that because there's nothing on a square root. You just don't have a square root by itself. You also do not have a log by itself. So what you're taking the log of is called the argument of the log. And one of our strategies is to set the arguments equal. Now, this is good for when you have 2 logs. I'm thinking the word logs might be underneath my head there. 2 logs isolated on either side of the equal sign. You could also say either side of the equation. But I'm going to write equal sign. Okay, so when you have 2 logs and you can isolate them on either side, then basically the logs as operators cancel each other out, and you can just look at the arguments and set the arguments equal to each other. But what if our equation doesn't fit either form? What if our equation isn't one log on one side of the equal sign all by itself, and it's not 2 logs that are isolated, okay? Now what do we do? So let's take a look at some examples. So here I have log base 2 of x plus log base 2 of 3 equals 4. So this has 2 logs, and I can't isolate them. So the only thing you could do there is you could maybe do this, well, like subtract log base 2 of 3 from both sides. And that would give you the log base 2 of x on one side. And then on the other side, you'd have this 4 log base 2 of 3. And that still doesn't work. Like, in order to change the form or to set the arguments equal, you can't have these other things in the middle of your equation. So that one does not fit either of our forms. It's not one log, and it's not 2 logs that can be isolated. Okay, similar. situation here. This one, the logs are already on either side, but you've got that plus 6. Now, it's important to note here, that's log base 3 of 4, and then the plus 6 is not part of the logarithm. So you cannot say 4 plus 6 is 10. Kind of like this, if you had the square root of 4 plus 2, you would have to do the square root of 4 to get the 2. You could not do the square root of 6, okay? Like that would be wrong. And most of you would recognize, well, that's wrong because the 4 is under the square root and the plus 2 is not. Same situation right here. The 4 is part of the log and the 6 is not. Now you might be wondering, how am I supposed to know that, Ms. Taylor? Well, if they were both part of the log, you would have to see the parentheses. Okay, so taking the log is order of operations precedence over the addition. So you would take the log of 4 and then you would do the adding. If you wanted to do the adding first, you would have to bump it up in your order of operations by putting parentheses on it. So that's how you would know. And the same situation there. We have these two logs, and they're on either side of the equal sign, but they're not isolated because you've got that plus 6 there. And then we have this one. We have the natural log of 2 plus the natural log of x is equal to the natural log of 4. And this is an equation that actually has 3 logarithms in it. So I lost my cat, so now I have 2 hands. That makes it so much easier. Okay, so we have 3 logarithms. Now, some of you are probably looking at this and immediately you're thinking, I know something I could do. And that's great, okay, because that means you're already on the next slide. Like you see it and you're like, wait a minute, I could do something with this. And you're not wrong. Yes, you can. What can you do? We can use the properties of logs to rewrite the equations in a form that will work. And so we spent the last 2 classes tinkering with these properties of logs, ways that we can add, subtract, raise them to a power, basically rearrange them. We can expand them and we can collapse them. Now we're going to use those properties to get these equations into a form that we can use. So this particular problem, we're going to use this property here, and I'll take a moment to just refresh it. If you have the log of x plus the log of y, you can multiply your arguments. So that would be the log of xy. So in our example, we have log base 2 of x plus log base 2 of 3. So I can multiply the arguments and get log base 2 of 3x. Now, I didn't write x3 because that's just awkward. So 3x, but essentially you can multiply the 2 arguments together. And now we've successfully rewritten that as one logarithm, and now I can use that first strategy, change the form. So this would be 2 to the 4th power is equal to 3x. I would go ahead and grab my calculator if I need to. 2 to the 4th power is 16. And now I can divide by 3. And I get x is equal to 16 thirds. And half of you freak out because you're like, no, a fraction, it can't be right. No, it can be right. And if you're not sure, you can grab your phone. This would be an acceptable time to use Photomath. Okay, and so, I have a equation on there from earlier today. All right, so I'm gonna Photomath it. And it tells me, you probably can't see it, but it does tell me that the answer is 16 thirds. So that's an appropriate use of your technology. That's an appropriate use of Photomath. So you do the problem out, and then you're going to run it by Photomath. Now, if Photomath gives you a different answer, then it might be worth it to go look at the steps, because that might help you find out where you went wrong. But you don't go back and erase what you did and copy down work you don't understand. So I was doing Photomath earlier today on some of the properties to see what Photomath would do, and it was kind of crazy. So don't, it's like the way only like a computer would do it. It's not the way a human would do it. And you don't want to get into the weeds there, but certainly to check your answer and see if you landed in the right spot or whether you need to ask a question in class. Okay, here's the second one. Now this one, we've got the logs on both sides, but they're not isolated. So what I'm going to try to do is collect the logs together and leave the 6 alone. So I'm going to start this by subtracting log base 3 of 4 from both sides. So I'm going to subtract it from the right because I want it canceled out to just get the 6 by itself. And then over here, I'm going to subtract it on the left. So that gives me log base 3 of x minus log base 3 of 4, and that is equal to 6. And now you might see something that you can do. Like, oh, I've got logs that are being subtracted. And you might recall that if you have log x minus log y, so you have two logs that are being subtracted, you actually can divide the arguments. So this could be written as log base 3 of x divided by 4 is equal to 6. And now we have gotten it into a form that we can kick in one of our strategies. So log base 3 of x over 4 equals 6 can be rewritten as an exponential as 3 to the 6th power is equal to x over 4. I don't know what I was thinking when I wrote that problem. You got 3 to the 6th power is 729. Okay, not one that we see a whole lot. And then we're not going to freak out about the fraction there because fractions just mean division. So if I'm dividing by 4 and I want to undo it, I can multiply by 4. And that is 2,916. The number everyone was hoping for. 2,916 is equal to x. And just because I am having fun in this lesson, I'm going to photomath it again. Oh, 2,916. Amazing. Your math teacher can do math almost as well as photomath. Feel accomplished. Okay, let's move on to the last one. So this one we have 3 logs. Now you can actually do this the same way that we did the last one, but it's like where you put all the logs on one side and then collapse them. I guess maybe if I feel like it, this is going to be a really short video, so so maybe we'll do it that way too. But in this one, if I just take the 2 logarithms that are on the left side, the natural log of 2 and the natural log of x, I can combine those together using that first property. So log x plus log y is equal to log xy, which in this case would end up being the natural log of 2x is equal to the natural log of 4. And now I've got 2 logs that are isolated on each side, so I can kick in that second strategy. So I would end up with 2x is equal to 4, and then we'll divide both sides by 2, and we get x is equal to 2. And because I am on a roll tonight with photomath, actually, it's been a really long day, and I'm kind of having fun. And don't do this. Don't do this the photomath way. I just expanded it to look at the steps. You know what? We're going to do this. This is what photomath does. Okay. So I'm just going to leverage this. So what they do is they do the natural log of 2 plus the natural log of x. And then on the other side, they turn the 4 into 2 squared. Okay. So they take the 4, they replace that with the 2 squared. Now everything on the left stays the same. And they're going to use the property that allows you to bring the coefficient down front. Okay. And they get 2 natural log 2. Then what they do is they're going to subtract the natural log of 2 from both sides. So they're going to get natural log of x is equal to 2 natural log 2 minus essentially 1 natural log 2. And 2 natural log 2 minus 1 natural log 2 is just natural log 2. And then they're going to use that property that allows them to set the arguments equal, and they will get x equals 2. Okay, now because I'm on a roll here, okay, don't do it the way that it is on the right. Okay, the way that's on the left is way easier, it's shorter, it's more it's just, it doesn't involve as much stuff. And this is where Photomath can be a great resource for checking to see if your answer is correct, but it is not always a great resource for working out the steps. And it's definitely not what you want to do to be like copying your homework to say, oh, I got a 10 out of 10 on my homework. Don't do it that way. Just don't. It's just don't. Taking a picture of that. Okay, now before I leave this though, because it's going to be a short video anyway, I'm going to erase this and we're going to pretend like it never happened. You can do this just to show that there are multiple ways to do it, and some of the ways are better than others. Kind of a big fan of the way I taught it. Is you could do this. You could do the natural log of 2 plus the natural log of x, and then subtract the natural log of 4 from both sides, and that would leave you with a 0. Now you can use the properties of logs, and we can merge these two together. Okay, and that'd be the natural log of 4. And then if you're subtracting, that would become division, so it would be 2x over 4 is equal to 0. This is a bad way to do it too. And now we can change the form. Now remember that the natural log is log base e. So it would be e to the 0 equals 2x over 4. Anything to the 0 power is, I'll let you think of the answer first. 1. And then we'd multiply both sides by 4 to clear that 4 out. And we'd get 4 equals 2x. And then divide both sides by 2. And 2 is equal to x. Don't recommend that way either, but the advantage to looking at it that way is that it does allow us to review what a natural log is, and allows us to review another one of those properties, and to review the idea that when you subtract everything from one side, you do end up with a 0 on that side. Honestly, this is the best way. Do it that way. All right, so now it's your turn. Like I said, this is a super short video, so try them. Feel free to check them on Photomath, or just kind of hang out until I'll go over these. So pause the video and then unpause it when you have some answers. Okay, so let's see what we've got. For number 1, we've got log of x minus log of 2 is equal to 1. So if I'm subtracting logs, I would change that to division. So that would be log of x divided by 2. And remember, when we don't see a base, the base is 10. And so this becomes 10 to the first power equals x over 2. And just like in the last one that we saw, we can undo that by multiplication. 2 times 10 is 20. And so x is equal to 20. All right, next one. I would combine the two logs on the left-hand side. So log of x plus log of 7 would give me log of 7x. So this would be log of 7x equals log of 37. And now I would use the second strategy. So 7x is equal to 37, and divide both sides by 7 to get x is equal to 37 over 7. That is a 7. That is a terrible 7. That's better. All right. Now on, ooh, this is a good one. And I don't know if I have enough space for it. Okay. So on the left-hand side, I have log base 6 of x plus 1 minus log base 6 of x. And then on the right, log base 6 of 29. So probably I'm going to use the same strategy that I just used, except with this subtraction, I am going to end up with a division problem. So I'm going to have log base 6 of x is equal to x plus 1 over x. There we go. Log base 6 of log base 6 of x plus 1 over x. And that'll equal to log base 6 of 29. And now I can set my two arguments equal. And this is a great problem because it actually taps into some material that we haven't covered yet, but is necessary to at least look at before your EOC. So this kind of equation is what's called a rational equation. Rational, of course, means ratio. So like you can hear the word inside of it, and a ratio is just another way that we can describe a fraction. So a fraction is a ratio. So when you see that like big fraction there, I'm looking at my cats playing with my shoes, then you know that you're dealing with a rational equation. Now remember that a fraction bar is just division. So I can undo this fraction bar here by multiplying. Now think, what was I dividing by? I was dividing by x. So how would I undo that? Well, I would multiply by x. And on the left, if I divide by x and I multiply by x, those cancel each other out, and I will be left with, x plus 1 on the left equals 29x on the right. And now I've got it to a linear equation. I will subtract one of these x's from each side to get 1 equals 28x, and then divide by 28. And so I have no place to write this answer. X is equal to 1 over 28. So my answers here are kind of hard to see. That's the answer to the second one, and there's the answer to the third one. Okay, that slide is a mess, but some good problems. All right, so that leaves us with your homework, mixed exponential and log equations. So this is a hodgepodge of stuff that we have covered in the last several lessons. So just a quick rundown before you guys just go off and do it. First one is a log equation based off of like the lesson a couple lessons ago. This is an exponential equation, and you'll have to use a logarithm to solve it. This is another log equation, but this log equation will require you to use some properties of logs. This is another exponential equation, and it will use a natural log. Here's a logarithmic equation. You can change the form. This is an exponential, and you can use either a log or you can change the bases. I would prefer that you change the bases. And then this one is an exponential equation, but you're looking to find the t-value there. Don't let the decimal throw you off. The decimal is because everything's going to work the exact same way. If you're more comfortable, you can switch the order, so you can do 7e to the 0.03t equals 1400 and just kind of switch the order on that. All right, so that's a rundown on that. You guys know where to find me if you have questions, and I will see you in the next one.